which is email service provider, and wanted to have a scalable email storage. And after later, the project was open sourced and now available on GitHub. So some of you may think, well, what's the problem with the email? Because most of the companies have Exchange and it handles it quite well. In most of the cases that's true, but in some cases when you have a huge volume, so just to give idea, that's according to the research. So at the moment, roughly every second, we have 4.5 million messages flowing around. And if you look at this number from email storage point of view, it's actually double, because every time you send the message, it's stored in your mailbox and stored in the recipient's mailbox. So now imagine companies like Gmail, Yahoo, Yahoo Mail, how much traffic they need to handle. And every time there's messages, write requests, and read requests. So the classic email storage system probably will look something like this, very simple. There's a mail transfer agent, and then there's a local delivery agent. Mail transfer agent responsible for accepting, queuing, and sort of doing a sort of virus scanning, spam analysis, etc. And local delivery agent is actually responsible for delivering and storing and persisting on the storage. In some cases, these two systems coexist together, like in Microsoft Exchange. So the problem that appears that when we started actually building project, we look at the most existing free and the most existing commercial projects, and we realized that almost all of them store metadata in some sort of database, whether proprietary or can be MySQL, and they store the messages as a file, or they store it also in database. And file system and database, they don't really scale well, as we know. So we had to come up with some sort of solution where we wanted to scale email storage on very cheap hardware, on literally by adding a pizza boxes, 1U servers, and scaling from 3, 5, 10 nodes to thousands. So that was sort of our objective. And this is what we came up with, very high level view. So we have, after MTA, so we're only implementing here local delivery agent, which just stores the messages on the storage. So we have here n number of nodes, ElasticInbox nodes, and each of the nodes responsible for accepting message and storing metadata on Cassandra cluster and the original file in the blob store. Obviously, to do this, we had to have all components being scalable horizontally. So we chose Cassandra mainly for that reason. I'll come to that. And from that point, basically, I want to just to give you an idea. I'll talk firstly a little bit briefly about why we chose not to store blobs in Cassandra and why we're storing actually blobs in the blob store. That's the first part. And the second part, I'll talk about the data model we used in the Cassandra. So why Cassandra? Well, Cassandra, as you know, scales horizontally. It scales really well horizontally. It doesn't have any single point of failure. It's highly available, and it does automatic replication. That basically gives us this possibility to just add more nodes and scale to thousands of nodes without any problem. Flexible schema, which means you don't have to define in advance how your schema will look like. So you can basically add different values, and it works really well with emails, because in some emails, for instance, you may have subject, in another one you may not have subject. So you don't have to fill in this field. Counters. This is interesting part, because that was there are plenty of NoSQL database out there, and there are also document stores. But one of the reasons why we chose Cassandra was counters, because we had to count things like the storage used by every user, a number of emails in inbox or unread mails, etc. So counters was really important for us. And finally, email storage. Well, Cassandra is really well at the writes. So if you're predominantly doing writes, it means that you should look at the Cassandra. And interestingly, this email storage does more writes than reads. And the reason for that is because if you look at your inbox, you probably get more spam every day than other things, than useful emails, and you never read them. They're just written once, you never read, and then they delete it, which is another write. And things like send email, every time you send email, it's also stored, but sometimes you read them, but not all of them. Notifications, you know, recently the email traffic was dominated by notifications from Facebook, from Twitter, other social networks. It's also quite a huge portion of traffic. And in mailing lists, I'm getting tens of emails every day from Cassandra mailing lists, so I'm not reading all of them. So that's why you get more writes than reads. So why we haven't chose to use Cassandra to store blobs, the raw email files. One of the requirements is to store the original files, is because users who are downloading from POP3, from IMAP, and other clients, when we're using for attachments, we have to keep the original raw file. So that was one of the requirements. So Thrift doesn't support streaming, so which means you cannot stream data from Cassandra. It has to load all the value of the column into memory to serve it. And by default, Thrift comes with a 5 megabyte limit, which you can change, but it's sort of not very sort of soft limit, if you want. So first we look at a possible solution. Well, let's split up a file into a number of chunks and store them separately, which did work, and we tried that. And the fact that we actually had only less than 2% of email traffic in our case, specific case, was more than 1 megabyte. So it kind of worked for us. But first of all, we didn't want to build a specific case solution. We wanted to have a more generic case. And if you look more on the enterprise email service, you get more messages which are larger than 1 megabyte than in our case. So the first reason is wasted RAM. So imagine the case when you, let's say, have to read or write 200 messages, each megabyte each. 5 megabytes each. So what will happen? Cassandra will load 200 of those messages into the heap, and 1 gigabyte of your JVM heap will be wasted. It's sort of not the usual use case maybe, but it sort of makes application vulnerable to this sort of attack. So if someone just sends a lot of large messages, it will affect the whole other users of the system. And wasted disk space. The thing is, as a rule, when you store data in Cassandra, first of all, it's replicated to the number of replicas, so you need to multiply it by the number of replicas. So if, let's say, usual typical case, or in our case, it was replication factor was 3. So imagine if when we're writing 1 megabyte, so automatically we get 3 megabyte used across the cluster. And then you need to multiply it by 2, because you need to have twice free space, just in case for a compaction, because compaction may take up to twice. So 1 megabyte actually requires 6 megabyte of storage. So when you're writing 1 megabyte of data into Cassandra across the whole cluster, you need to allocate 6 megabytes of space. Now, when we're talking about megabytes or even terabytes, maybe it's not that important. But when we start talking about tens of terabytes or 100 terabytes or even petabytes, then it's becoming expensive, because you're wasting a lot of disk space. Also, you waste CPU, because every time you store data in Cassandra, there's a compaction process which goes through it and does sort of puts in a sequential order, etc., and it uses your CPU time. There's new leveled compaction strategy in version 1.0. It wastes less disk space, but it comes at the price of more I/O. So we haven't really tried this one, but it's also not free. So after looking around, we decided to use blob stores actually to storing blobs. First of all, because blobs are designed to storing blobs, as you can tell from their names. and they can store unlimited number of objects in a single container. The examples is good example, Amazon S3, probably most of us have used that. And then another one is open source, free one from OpenStack, the object store called Swift as well. And we actually support, ElasticInbox supports 15 other through JClass. JClass is basically a library which provides you with an abstraction layer, and you can store on any supported blob store. It would give us, in addition to memory and I/O, the main concern of ours was disk space. It would give us 40 to 50% more disk space because we don't have to care about this compaction. We still need to do a replication factor because the blob store, particularly the Swift, the OpenStack one, the design was very similar to Cassandra. It has the ring, continuous hashing with the ring. It has tombstones when files deleted, and the other replication mechanisms. It's very, very similar, but the difference is it doesn't store them in a SS tables. It just stores them as a file, and that's actually the cons of blob store. At least OpenStack and S3, they tend to be much slower than Cassandra, because in Cassandra, when you do write, it first writes in the memory and acknowledges the write. It's okay. But blob store actually needs to write a disk. And this is where the blob store became sort of bottleneck for our application. And that's why we're now looking in the next version to support some sort of hybrid mode, where we would store messages less than, let's say, 50K in the Cassandra, and everything above the 50K in the blob store. That would give us, we estimate that roughly 50% of our traffic is less than 100K. So if we put those 100K files, we already get about 2 times of speed up. Now, final word about the blob store. Oh, that doesn't look very well here. But there was recent an article by Martin Fowler, and he's basically saying, an article called Polyglot Persistence. The term originally was coined back in 2008, but what he was basically saying is that we will see more and more companies adopting different types of storage for different types of data. Because Cassandra is good, but it's not a silver bullet. You cannot solve all your problems with this. And here, in this article, I took this picture from this article. You can see it very well, but for instance, it shows us financial data. You probably use RDBMS for financial data. And for analytics stuff, this is really just example. That doesn't mean that you should use this. It's just an example. For instance, for recommendations, you would probably go, here's a Neo4j, which is a graph database, etc. I'm just added the blob here, that if you really need to store blobs, you probably would better choice for you, if they're large enough, better choice would be to use blob store. Okay, so data model. So the classical way to design NoSQL data model is to look at your data access patterns, how you use data. That's the radical difference between the SQL. And in our case, we had email messages which are immutable. So once you've got the message, it never changes. It doesn't have versions. There's only one version of each email, and it's there. You can move it from one folder to another and do some different things, but it's still there. And mostly very recent messages are accessed. So if you have, let's say, 2,000, 3,000 emails, you only access mostly the last 1,500 messages. You don't go back. Well, you can go back, but often you don't read those. So that's why we're storing them by time, ordered by time. I'll come to this. But sometimes it's actually vice versa. Its access patterns are driven by NoSQL data model. What this means is that NoSQL data model has certain limitations. And if you want to use it, you have to adopt your access patterns to this. And the good example is, well, yeah, basically you need a synergy between your programming model and your data model on storage. And if you look at the classical example with RDBMS, what we usually do, we take data, we normalize it. We have when we reach the third normal form. Everything is nice in database, and then we create over the ORM the model in the application. And after that, everything is easy because objects and everything is clean. You cannot do the same thing with NoSQL because, as a rule, you denormalize data when you store it in NoSQL. And this is where the problem begins. And when we started doing this, we sort of took the classical model of emails, where we have folders and we have messages, and messages are in the folders, and all this sorting stuff by name, by subject. And we started modeling, we started writing the code. And at some point, we felt that something is wrong because the data is in Cassandra is not optimized for performance, and our code is very ugly. So we started thinking, okay, well, how we need to fix this? And it took us a while we realized that it wouldn't work like that, and we need to something alternative. And the alternative was alternative to folders and mails was just one, is Google Labels. And that was the moment when we realized, was aha moment when we realized why Google actually using labels and not folders. And I personally don't know much about Google's architecture, but it's just we did some little bit of reverse engineering, and my personal feeling is that the labels and some other features were driven by the limitations in big table. One thing is labels, and another thing is no custom sorting. Because before Gmail, every single email client would give you sort of functionality where you can sort by subject, by sender, by recipient, all that by size, by attach. Nothing like that in Gmail. Mails are just sorted by their arrival time. That's it. And that's also, when you look from the Cassandra point of view, that makes perfect sense. So we also sort of ditched this notion of folders, and we said, okay, we don't do custom sorting, we just sort by time, just like Gmail. And suddenly, data model in application, in Cassandra, became very clean, very robust, and everything started just going smoothly. So there are other examples for when your let's say functionality is driven by NoSQL data model, is when you have pagination, and you don't put basically pages like you have like 10 pages and you say 1, 2, 3, 4, 5 as you used to do. You just put a more button and you just click more and more and it just loads. That's also sort of, for me, it's driven by NoSQL, maybe not limitations, but sort of data model. Okay, so in our case, we have 4 column families. We have message metadata, which is the biggest one, where we store all metadata for messages. We have index labels, where we store indexes for labels. We have accounts and counters, and each account is basically identified by its email, very simple. Each message identified by a unique ID, which is time UID. And labels are just identified by integers, just per account. So this is how accounts looks like. So we have some sort of, for instance, reserved labels. And yeah, that's actually, if you notice it in Gmail, you have all mails folder, not folder, label. And what all mails folder label does is basically when you remove all labels from the message, it still keeps it there. So it's sort of a label, fallback label, where when you remove everything, this one still persists. So we have similar concepts of label ID 0, for example, all labels, and then the inbox, draft, etc. And by the way, the archive function is basically doing nothing but removing labels. So this is how index labels looks like. So basically, column family with a composite key. So it uses your account and label, and in each label we just store in ordered store time UIDs ordered by time. So, for instance, if you need to get last, let's say, 20 messages from inbox, You just do a slice query, and it will just give you last 20 message IDs in your inbox. So pretty much every time you access your inbox, it will do that. But it stores this custom index for each of the labels. So for instance, if you have some custom label and you have some messages in this, they will be, the IDs of the messages will be stored in it, but it just stores message ID. There's no value. This is purely for a purpose. This is just as a reverse index. So message metadata, this is the most probably sophisticated column family we have. It's super column family. It stores message metadata and pre-parsed content. So we're not only storing things like, for instance, the message headers and which label it belongs to, but we also extract the message body and store it in a compressed as a compressed binary value. This gives us the ability to basically show a user message without actually parsing it second time from the web interface. And I don't know if you noticed in Gmail sometimes when you open messages, it opens very fast. When you try to download the attachment, it takes some time. And again, this is just nothing more than speculation, but we think that they also store pre-parsed text and then they store separately somewhere the binary file, the raw message. So time UID as a unique message ID, and we order by time. So in Cassandra, when you have time UID, it automatically sorts it. Accounts, all metadata are on the same node. So one of the requirements, imagine if you have a 100-node Cassandra, if you wouldn't partition it properly, you may end up, for instance, when reading messages, you may end up, okay, let me show the next slide. So this is how it looks like. So if we would partition it by message ID in, let's say, in a cluster with 50 nodes, and I need to take 50 messages, there's quite a good chance that I will read from 50 nodes. And that's very big performance hit because all this network round trip delays, etc. So it's important to store all, in our case, it's more to store all messages on the same node. And that's why we actually went with the super column, because in super column, you can have a key and then a super column name. And in super column, you can have subcolumns. So a key would, your data would be basically distributed, partitioned by your key, and then ordered by your super column name. And that basically gives us the flexibility to store all the users' single accounts data on the single node. And when we read from the single node. Inside it looks something like this. So you have a from value to value. Again, because the scheme is flexible, for instance, here I have parts which are basically the JSON array of all my attachments. But if email doesn't have any attachments, I just don't have this record here, and that's it. And it doesn't take any space. So its schema flexibility is very nice. And we have labels and markers. Marker is similar to label, it's just not indexed, and it's shows whether message is new or replied, forwarded, etc. These kind of markers. So, and as you see, we store here the message content as well. This is here it's shown as a plain text, but actually it's compressed with LZF we use for that. In Cassandra 1.0, you know, there's already built-in compression algorithm. But the thing is, it's good for when you compress, it's good for reducing the storage size. But when you need transfer data between, for instance, in our case, between ElasticInbox nodes and Cassandra nodes, it will still take this network traffic because it's decompressed and transferred. In our case, we transfer and then decompress. So we save sort of network bandwidth by compressing the messages. So let's see. So why we couldn't use just let's say composite keys? So imagine the simple query. We need to get list of latest newest 30 messages in your inbox. Okay. So first thing we do, we go to our index labels, here, and I get the newest 30 messages, okay, with simple slice query. Looks like this, very simplified version. So I get a key, I know index, I know account, I know that it's inbox, and number. So I get IDs of the messages. Now in data, in message metadata, we store basically all messages, which means that there are messages from inbox, there are messages from, let's say, sent emails, there are messages which are in spam. And now we need to get only messages from inbox. So what we do a multi-get query on super columns. And we pass IDs basically, and it will extract only the records which we need from message metadata and send it back to us. So it would be 2 requests to Cassandra. One, get the list of messages in this label. The second one, get the metadata of these messages. With dynamic composite columns, it wouldn't be possible, because so this would look something like this. So message ID, and here instead of subcolumn, I would have it here in the column name, and then value would be here. So I can only slice it by the first part, or I can get the exactly one. So if I need to take this and this message, I have 2 options basically. Either know exactly all values of the subcolumns and send a list of precise subcolumns, or get the range from here to here, which would also include this one, which I don't need. So that would return me too much data. In some cases, it may return me extra thousands emails. So right now, the only solution is to use super columns and wait for version 1.2, where they will be seamlessly replaced by dynamic columns. So that the promise of Cassandra right now is that they will keep super column API, but implementation may change. So there's no need to avoid super columns, because some people religiously want to not use them, but it's actually fine. And in our case, actually, when you think the disadvantage of super columns is that the subcolumn part is always read and written all together. So when you just modify one of the records, it rewrites whole of the subcolumn. So that's a performance hit. But in our case, and maybe in your case, if you read and write all of these values all together, it's actually fine using super columns. So counters. Okay, that's an interesting one. That was sort of the reason why we chose Cassandra, counters. And we decided, well, we can use also super column for this. And that's how we initially designed it. We basically store for each of the labels, we store information like total bytes, number of messages, number of new messages or unread messages. And that gives us pretty much all we need to know about the email or your inbox. But as time goes, we basically under the regular load, there's no problem. But when we started putting or running, let's say, the batch jobs, for instance, delete all old messages from subscribers' inbox, we started seeing strange things. People started reporting that they have -5 mails. Some others saying that I don't have any emails, but I still have 5 new. So very strange things started happening. And we started sort of a bit research about the counters. And it turns out that the implementation of the counters in Cassandra it's sort of very specific. It's not the same as for those with RDBMS background. It's not the same as sequences. First of all, counters are non-atomic. What it means that every time you update the counter, you cannot get the exact value right after that. So you cannot do increment and get, basically. You can do increment, and then you can do get. And in between them, between these two operations, something else may happen. So you're not guaranteed that the value that you got back is actually the same value at the moment when you increment it. And this is basically due to the nature of how its counters are implemented in Cassandra. They are distributed. Because of that, you basically cannot have a unique sequence generator. For instance, if you want to have a sequence generator which would generate you unique numbers, you cannot use Cassandra counters for that. And it's quite easy to miscount. So, as you know, Cassandra is when one of the nodes fails, Cassandra just times out, or the node that you are connected, let's say, fails. Cassandra times out, and what happens then is that your library probably will retry to increment counter, this time through another. And the thing is, you don't really know if the node which failed actually incremented it or not. So you end up in a situation where you retry to count, and you either increment it twice or decrement it twice, which makes counting a little bit problematic. So it's good to use counters for things like add impression, page views, which you can tolerate, let's say, plus minus few views. But if you're planning to use financial data, count financial data or something like this, I would really think carefully here. So what we're doing now, we're basically trying to figure out how we can sort of prevent this. And one of the things is we increased timeout on the counters only when we do counters specific writes. And the other thing, we try to move away from super Coleman model to a Coleman model and not to touch too much records during the same update. So trying to minimize sort of I/O on the counters. Yeah. But there are good things about counters coming in the new versions. For instance, we are using 0.8 version, and I know that in 1.0 there's already some improvements with counters. Okay, so ElasticInbox was in production since 2011. Just some stats. So we have roughly 200,000 accounts running on top of it, with more than 30 million messages. And it's 4-node cluster, very small. Replication factor is 3, and as I mentioned, Cassandra 0.8 version. So the first thing that we liked about it is that when we loaded 1 terabyte of raw mails into into ElasticInbox with this data structure, the size across total size was 70 gigabytes. This is without replication factor. So if you calculate with the replication factor and number of replicas, you can multiply it by 3 and divide by 4. But 70 gigabytes. And we think the main reason for that is because, and note that we store actually metadata plus LZF compressed email text. But we think the biggest save was coming from the fact that when you store small files on the file system, it becomes very fragmented, and you have a lot of wasted space. But in Cassandra, it sort of writes them in a sequence in not one, but few big SS-stable files, and that sort of already does a great job. So here are some other stats. So we have roughly 40 requests per second per node. That's both reads and writes. And we see in average 10 millisecond read latency and 0.02 millisecond write latency. Cassandra is really good at writes. And write to read ratio per column family is just coming to the point which I made in the beginning, that email system actually does more writes than reads. The message metadata, we have 3 times more writes. In the labels, we have 2 times more. Others are not so important. So main email data is stored in these 2 column families. So just a few notes about the future work. So first thing to do, of course, we're trying to polish the performance of the system, and we will try to add full text search on top of Cassandra. And there are some implementations. We're just trying to sort of include them into ElasticInbox. But again, coming back to this polyglot persistence, we may end up actually in choosing something specific for searching if it would just perform better. Because right now there's only one implementation which I'm aware of, is Solandra. and it's sort of the state of project is not going as fast as we would like. So POP3 will be coming in the next release. It's pretty simple, straightforward. We'll be just adding it. Right now, we only have the REST interface. IMAP is a little bit more tricky because IMAP actually requires this thing which I mentioned about the counters. It requires a unique sort of method which will increment and uniquely give you ID. So that we think that would force us to use some sort of zookeeper for distributed locking. Built-in filtering rules basically will apply labels based on the rules, and message threads of conversations similar to the one you have in Gmail. That's basically another indexes on top of existing labels and message metadata. So that's pretty much it. As I mentioned in the beginning, the project is open source. You can access it, all the code from GitHub, and follow on Twitter. And any questions? Yep.
Earlier you mentioned about how you, I think it's the metadata compound. Do you ever get hotspots?
What do you mean by hotspots?
If it's a slide back. Yeah. So does that mean
2 wasn't enough, so we want, because we read and write with quorum, 2 for us was basically would mean for us that it would go down. 3 is something, the minimum for quorum, I would say. So if you have 2 replicas alive, you can still read and write, and it's seamless. So that was basically the main reason, to read and write with quorum. Yep. Yeah, we don't basically do this because in the beginning we thought about this, the duplication, but then we thought that, okay, NoSQL is known for denormalizing things. And when you're starting doing the duplication, basically you're adding extra logic and the extra processes that will need to take care of this. So for blob stores, there are blob stores that do this for you. So we just leave it for them. For Cassandra, we just denormalize it to the level where we don't care about the duplication. So it depends on the use case. Maybe in some use cases it may be very handy, but in our case we just feel that the more work and more resources would be used to perform actually the duplication than just denormalize and keep duplicated.
There's a slight tension here between, hey, denormalization is great, oh shit, it takes up too much space.
Yeah. But that's what's the factor? That's the thing. What's the factor would be of the duplication? How much space it will save? In our case, even if it's, let's say, 20%, that's not a big deal. So, yep.
what kind of utilization do you see across that time?
The most, well, basically we don't see much. It's less than it's pretty much idle, to be honest. Very little, maybe up 5-6%. But when compaction kicks in, then we get quite good, maybe 25. Depends on the number of CPU and number of cores basically you have. But we see one of the cores during the compaction being completely working on compaction. But you can configure this in Cassandra. You can throttle it.
Do you host on virtual instances?
No, we have a physical service. Yep.
You said that the counters were really important. I don't understand what you gain from standard relation with counters.
The counters was important for us in the sense that we were looking at NoSQL systems, not RDBMS. And within NoSQL systems, Cassandra was, I think it's still the only one that supports, maybe the others supported, but yeah, edge-based supported, but it's sort of based it's with the zookeeper and stuff. But yeah, you're right. The reason why we didn't go with the edge-based was that it just needs too much setup. There are too many moving parts, and we wanted to start really small with 4 or 5 servers, and have very simple setup. So HBase in our case was a little bit overkill. So
Okay, we better leave it there because we need to crack on with the next one. If everyone just say thanks for
okay.
watching.
Thank you.